Let's try a small experiment. Place your hand right in front of you and observe it closely. Now, without overthinking, answer immediately. Does that hand still exist when you're no longer looking at it? Instinctively, you'd surely affirm, yes, of course, because it has weight, a specific shape, and even a temperature. The universe doesn't need your eyes to keep all matter in its place, does it? You believe that, and I believed it for many years too. When I walked the halls of Caltech, I firmly believed that physics was the subtle art of describing a reality that already existed, just waiting for us to discover and measure. But I was wrong. No, not just a minor error. I was wrong from the smallest detail, completely wrong about the structure, and fundamentally wrong about the very meaning of existence itself. And so are you. What's even more astonishing is that physical science has known this truth for a long time. For nearly a century, physics has realized that your intuition about existence is just a brilliant lie, constructed by your brain to help you survive on the ancient African savannas. No, not only that, but also to help you somewhat understand this universe, I'm going to do something that many people have tried to explain but haven't dared to do. From this moment on, I will be completely honest with you. The truth is, Schrödinger's cat is not simultaneously alive and dead, as you might think. It's strange how that image has become an icon on t-shirts, memes, and even synonymous with quantum physics. That image of a semi-transparent cat suspended in a ghostly superposition between life and death is actually a distortion, an interpretation so terrible that Schrödinger himself was horrified by it. And the greatest irony, a cosmic irony that makes me ponder, is that Schrödinger created that thought experiment solely to demonstrate the absurdity if quantum mechanics truly operated in the way people mistakenly believed. Did you know that when Schrödinger proposed this experiment, he never intended for it to be accepted? In fact, it was a sharp rebuttal, a reductio ad absurdum to assert. If your theories lead to such bizarre results, then there must be something fundamentally wrong with how you're interpreting them. Yet, humanity's reaction was completely unexpected. That's amazing! Let's print it on t-shirts! However, did you know there's something even more terrifying than misunderstanding Schrödinger's cat? What should truly concern us isn't the erroneous visualizations, but the astonishing truth hidden behind the correct understanding of it. Because once you truly grasp what Schrödinger intended to convey, once you understand the real nature of quantum superposition, you will confront a truth far stranger and more terrifying than the image of a cat that is both alive and dead. You will have to accept a startling possibility, that reality, as you've always imagined it, might not exist at all until someone observes it. And believe me, that will change everything you thought you knew. Try closing your eyes for a moment and imagine a coin spinning rapidly in the air. What do you think? Is it heads or tails? And before it lands, does it already have a definite side? Your natural, instinctive reaction would probably be, oh, it's definitely in a specific state already. I just don't know what it is yet. As if a predetermined answer is hovering somewhere within that piece of metal, just waiting to be revealed. In other words, you think that uncertainty belongs to you, to your lack of knowledge, rather than to the coin itself. That is the essence of classical determinism, also known as the clockwork universe. A world where everything has its precise place, and our ignorance is the only barrier to predicting every event. But there's a shocking truth. The entire universe, as conceived in that way, doesn't exist. It's not that we're not smart enough to understand it. It simply isn't real. And astonishingly, quantum mechanics, the most precise and successful theory ever devised by human intellect, has unequivocally stated something that would send shivers down the spine of any 18th century philosopher. Uncertainty doesn't belong to you, but to the universe itself. What I'm about to reveal to you now isn't the cat story you've always heard, but the hidden truth behind what actually happened when Schrödinger wrote that fateful letter in 1935. We'll explore what truly happens in a quantum measurement and why the correct answer has caused such a deep division among the world's most brilliant physicists today, all over what seems like the most fundamental question we can ask: what is reality? Did you know that Schrödinger never intended his experiment to be an illustration of quantum mechanics? On the contrary, he created it as a refutation, a vehement protest. So, if the image of a cat being both alive and dead is just a misunderstanding, what was Schrödinger actually trying to describe? And why is that correct description something textbooks often shy away from, far more unsettling than the t-shirt version we usually see? Back in 1935, a silent intellectual battle was unfolding, not the one you might think would come later. Although a fierce debate that had raged for a decade in physics conferences through letters between Einstein and Bohr and echoed in the halls of Göttingen and Copenhagen was also reaching its climax. Have you ever wondered what the true nature of reality is? The battle for its definition is still ongoing, perhaps never-ending, and astonishingly, a mathematical equation lies right at the heart of that controversy. So, what does the Schrödinger equation do? It reveals how a wave function, a strange yet incredibly important mathematical concept containing all possible information about a quantum system, evolves over time. It sounds complex, but this is the key. But wait, the real problem isn't the equation itself. What truly puzzles scientists is what is the deeper meaning behind it. Let's try a thought experiment. Imagine a single electron. You'd surely want to know its exact position, right? However, quantum mechanics doesn't claim that the electron is at a specific position that we simply don't know. Instead, it reveals a completely different truth, one that is far more perplexing and thought-provoking. Can you believe it? The electron doesn't possess a definite position at all until we perform a measurement. Before being measured, it exists in a strange superposition state, simultaneously in all possible positions, each with a certain probability, all meticulously described by that mysterious wave function. So ultimately, what profound meaning does this hold for our reality? Surprisingly, there are two possible answers to this mystery, and what's even more fascinating is that depending on your choice, you'll find yourself living in entirely different universes. The first possibility, the electron truly has a definite, clear position, we just aren't capable enough to know it. According to this view, the wave function is merely a convenient mathematical tool reflecting our lack of information rather than the true nature of reality. In other words, that uncertainty belongs entirely to our perception. This interpretation is known as the hidden variable interpretation. Even the great Albert Einstein was so fond of this view that he dedicated the last 30 years of his life to persistently defending it. However, there's a harsh truth. This answer is almost certainly incorrect. So what about the second possibility? This is the answer provided by standard quantum mechanics. From this perspective, the wave function doesn't merely describe our lack of knowledge, it is a true description of reality itself. What's astonishing is that reality, before we perform any measurement, truly exists in an indeterminate state. There are no hidden answers waiting to be discovered. Can you believe that the position of an electron doesn't actually exist until the moment we measure it? Try to imagine, at its most fundamental level, our universe is a place filled with inherent uncertainty about the very existence of things. When you perceive a crack in understanding, rest assured it's not a flaw in physics. The field remains entirely robust. So where is that crack? It's deeply philosophical, hidden beneath every intuitive perception we have of this world. But what turned that crack into an abyss? It was an experiment that dealt a fatal blow to determinism, more powerful than any philosophical argument ever made. Have you ever heard of the double-slit experiment? Imagine we fire individual electrons at a screen with two slits behind it, and behind that there's a detector plate to record them. According to conventional logic, if electrons were just billiard balls with clear positions, you'd only see two lines, each aligned with a slit. But strangely, we don't see that. Instead, an interference pattern with alternating bright and dark fringes appears. What does this mean? It seems the electron passed through both slits simultaneously, interfered with itself, and ultimately landed at a position dictated by that interference. But there's a problem. Each electron is fired individually with no teammates to interfere with. So how do we explain this phenomenon? The only way to account for that pattern is to accept that the electron literally passed through both slits. This isn't a metaphor, it's an accurate description of what's actually happening. Do you find this hard to believe? This very fact has driven many scientists mad with incomprehension. What happens if we try to peek? If you place a detector in one of the slits, or add any mechanism to know which slit the electron passed through, the interference pattern immediately vanishes. At that point, the electron behaves exactly like a regular billiard ball. So what's the condition for the interference to disappear? If the universe contains any information about which slit the electron passed through, then the interference phenomenon ceases. Conversely, if that information doesn't exist anywhere in the universe, this leads to an incredible conclusion. The interference appearing in the universe seems to know whether it's being observed or not. Are you feeling dizzy from all this? This is precisely where Schrödinger enters with his famous 1935 letter. Have you ever wondered if a scientist could use sarcasm to challenge an entire theory? With a gesture full of irony that his contemporaries could hardly grasp, he stated, "All right then, let's take an electron in a superposition state. And what happens next? Let's link it to a system where, when that electron decays, it triggers the breaking of a vial of deadly poison." Sounds crazy, right? Now, place this entire setup into a sealed box with a cat and close the lid. And here's the astonishing part. Based on your arguments, the electron will be in a superposition, the mechanism will be too, and the vial of poison will be no exception. And the culmination is that the cat exists in a superposition of life and death. But do you know what the most crucial, often overlooked part of this story is? He always stressed, this is ridiculous. So what was the true meaning behind his words? He wasn't trying to say, look how weird quantum physics is. Rather, he was asserting, if your theory leads to this outcome, then it has a serious problem when applied to the macroscopic world. What truly happened? There must be some factor that prevents this superposition state before it affects the cat, and you still haven't been able to identify what that is. So what ultimately is the answer modern physics found? That factor has a name, and it doesn't claim that the cat was alive or dead before the box was opened, nor that it was simultaneously alive and dead. A surprising truth. It reveals something entirely different, something that has never appeared on any t-shirt. Surprisingly, Schrödinger presented the cat example as an argument to demonstrate absurdity, but modern physics reacted in a way that even he couldn't have foreseen. And what was discovered? Scientists seriously considered that seemingly absurd idea and found that superposition truly exists at the macroscopic level. However, the meaning of this superposition is not what you might imagine. So what's the crux of the matter? It's the crucial difference between a misunderstanding and an accurate understanding. Do you realize its significance? This isn't just a minor difference, it's the boundary between a purely philosophical curiosity and a truly serious existential crisis. To truly understand, what do we need to do? I urge you to temporarily set aside the image of the cat, the box, the poison vial, and especially that entire dramatic scenario. Why? Because that entire setup was designed to lead us to a false intuition. What will be the consequence? If we keep clinging to that visualization, we will constantly fall into misguided thoughts. So let's rediscover it from the beginning. What, after all, is quantum superposition truly? Do you know what extraordinary thing a quantum system can do? For instance, an electron can exist in a state that is a sum of many different possible states. But be careful, don't misunderstand. This doesn't mean it's in one of those states, and we simply don't know which one. So what is it then? In fact, it exists in a state that we cannot intuitively name because there is nothing analogous in the entire human experience. Have you ever wondered if there is a state that exists solely in the abstract mathematical realm of Hilbert space? So how do we truly know that it is real or merely a gap in our own understanding? So where is the evidence? The classic double-slit experiment through the phenomenon of interference clearly demonstrated that. Try to imagine, if an electron truly possessed a definite position that we simply don't know, could it interfere with itself? The answer is no, it couldn't. So what does this interference pattern reveal? It is powerful empirical evidence asserting that superposition is an ontological reality truly existing, not merely an epistemological concept. But what happens next? When you measure the electron, an extremely strange phenomenon suddenly appears. What's astonishing is that the wave function doesn't evolve smoothly as one might expect. Instead, it abruptly collapses discontinuously. And from countless potential positions, the electron suddenly chooses to appear at a single point. What happened? The remarkable thing is that this individual result is completely random, an irredeemable and unpredictable randomness. Can you believe it? No one in this universe and no known scientific theory can tell you exactly what that result will be. What's the only thing we can know? It can only tell you the frequency with which you'll get each result, not the specific outcome. And this is what astonished even a great mind like Einstein if you repeat this experiment many times. The controversial point isn't that physics is technically incomplete. Rather, if the standard interpretation is correct, then our universe is fundamentally indeterminate. Can you accept that? This deeply violated what he considered almost an indispensable philosophical necessity, that reality must exist independently of our observation. Was he right? So what really changed the game? This is the part that completely transformed everything in the latter half of the 20th century. To solve these mysteries, physicists developed a groundbreaking concept, quantum decoherence. What is it? So what does decoherence explain? It says that the reason the cat isn't both dead and alive isn't because quantum mechanics stops applying at large scales. So what is it then? The important thing to remember is quantum mechanics always applies to everything without any exceptions. So why don't we see quantum effects every day? What's the real reason behind this phenomenon? It's completely different. Imagine the macroscopic objects we see are made up of trillions of particles. These particles constantly interact with their surroundings, from photons in the air, gas molecules, to temperature and everything else. Did you know that in the world of quantum physics, every interaction is a measurement? Amazingly, every tiny particle in the environment, upon contact with a larger system, immediately gathers information about that system's state. So what happens when information is stolen? Immediately, that strange quantum superposition state is broken, dissolves, and completely disappears. But are there any exceptions? With a perfectly isolated electron, that unique superposition state can still be preserved. However, think about a cat. With approximately 10^27 particles constantly interacting at room temperature, decoherence happens incredibly fast, in a moment many times shorter than even the Planck time. In other words, this phenomenon occurs instantaneously with no delay whatsoever. So what conclusion does this lead to? In reality, the cat never truly existed in that strange superposition state. Why is that? It's not because quantum mechanics doesn't apply to cats, but because a cat is too large a system, too entangled with its environment, causing its wave function to collapse even before you can wonder. So what's actually happening inside that mysterious box? Do you think the cat is both dead and alive, waiting for you to open the box? That's not the reality. So what is the truth? The entire system, from the cat, the mechanism, the poison, the box, the air, to the photons, all become entangled in a colossal, global quantum state, so tightly linked that the boundary between what is observed and what is not observed becomes meaningless even before you open the door. However, has decoherence resolved all the issues? Unfortunately, no, it hasn't completely solved the problem. So what does it explain? It helps us understand why the world appears classical, why large objects have definite positions, and why you never see a cat in a superposition state. But there's a deeper question it can't answer. Exactly when and how does the superposition of countless possibilities collapse into a single definite reality? And that question, going beyond the image of the cat, the box, or the poison, remains a great unsolved mystery. Are you ready for some surprises? The answers physicists offer are so radically different, so profoundly unsettling in their implications, that you'll need an entirely new map to navigate them, a map that bears little resemblance to the universe you thought you lived in. Decoherence can explain why we never see a quantum cat, but it still can't explain why you get this specific outcome rather than another. It can't explain why the universe chooses a particular outcome. And the interpretations that attempt to answer this question lead to conclusions so divergent that it's impossible for all of them to be true. Or perhaps the very question we're asking is flawed from the start. And among these interpretations, there's one that stands out. It's the most radical, the hardest to accept, yet the most mathematically honest. Do you want to know what it is? Are you ready to confront an unbelievable truth? Prepare to completely abandon the notion that the universe is merely a specific place, not metaphorically, but in the literal sense of the word. So what if quantum mechanics, with all the evidence supporting it, is actually correct? In that case, the universe is no longer just a simple three-dimensional space containing all events. Instead, imagine this. The universe is actually a colossal quantum state, a complex universal wave function, a mathematical entity existing in an infinite dimensional space. And it evolves in a perfectly predictable way according to the Schrödinger equation. And astonishingly, within that grand mathematical object, what we call reality, what you're seeing right now on your hand, turns out to be just a faint shadow, a projection, or even just a tiny branch. How do we grasp this idea? We need to explore one of the strangest yet most honest interpretations of quantum mechanics ever proposed, Hugh Everett's theory, which he put forward in 1957 as a PhD student at Princeton. Everett proposed a shockingly simple idea. What if the wave function never truly collapses? And what if the Schrödinger equation is always true for everything, without any exceptions, including measuring devices or the observer themselves? So when you perform an electron measurement and get a specific result, what's actually happening? The system, comprising the electron, the measuring device, and yourself, collectively enters a superposition. In one state, you'll observe the electron at position A. In another state, the electron appears at position B, and you are also observing that position B. What if both of these states exist with equal reality? Exactly. This is the foundation of the many worlds interpretation. When first hearing about this, many people often immediately think of science fiction stories, where parallel universes float somewhere in another space. However, that's not the idea Everett proposed. He didn't say that parallel universes exist in some place in space. In fact, there's no spatial separation between them, nor is there a multiverse encompassing them all. So what did he really mean? He meant that the universal wave function encompasses all possible outcomes. And when a measurement is made, the universe splits into multiple branches. In each of these branches, a different version of the observer witnesses a completely different outcome. Think about this. You are not just a tiny point in space. Instead, you are a branch in a colossal tree structure of countless possible configurations. And at this very moment, as you're listening to these words, the universe continues to split, creating countless new branches. Each new branch describes a distinct version of every quantum measurement occurring throughout the universe. And the astonishing thing is, all these branches exist just as genuinely. So what truly bothers you isn't the number of universes, but this question. If every branch is equally real, why are you existing in this particular one? Have you ever thought that sometimes the problem isn't the answer, but the question itself? Everett once asserted that, what if I told you that there isn't just one you existing in this reality? In fact, there are countless versions of you, each in a different branch of the universe. Every experience you have in a specific branch of the universe isn't just an event. It's also what shapes the meaning of being that particular version of you. Isn't that fascinating? Let's pause for a moment together so this idea can truly sink in. Have you ever wondered if the multiverse theory is true, whether there are versions of you who made completely different choices or were somewhere far away when a life-changing event occurred? These aren't fictional possibilities, but actual branches of the universe's wave function, sharing the same physical state as the version of you that currently exists. What does this mean for you? Instead of having to choose between possibilities, the universe did something incredible. It embraced everything. Don't you find that magnificent? But is this the only perspective? Certainly not, because there are still other interpretations waiting for us to explore. We have the Copenhagen interpretation, a theory suggesting that collapse occurs during measurement. But the interesting thing is, it deliberately avoids defining what a measurement truly is. Don't you find this confusing? It might work effectively in practice, but philosophically, is it truly satisfactory? The answer is probably no. Can you imagine a contract that functions smoothly, despite having an extremely vague clause that no one wants to delve into? This situation is quite similar. So what about Bohmian mechanics? This theory proposes a fascinating idea. Particles always have definite positions, but they are guided by an invisible real wave that moves through space. Do you believe in this? Although it restores determinism, it comes with a challenging concept, an instantaneous non-local pilot wave. This seems more complex than you might think, doesn't it? Imagine a wave that knows everything about the entire universe, everywhere, all the time. This would certainly make a genius like Einstein incredibly puzzled and uncomfortable. Don't you agree? And then we have Rovelli's relational interpretation, a perspective that quantum states are not absolute properties of a system. So what are they? They are merely relative. This means they only truly make sense when viewed by a specific observer. So how important is the role of the observer?